Okay, so for homework 9.1 here, I'm not going to have time to do a full video, so I went ahead and scanned my keys and we'll discuss these a little bit as we go through, but I am going to try to move through pretty quickly as well. So the key concept with question 1 here, right, to determine whether it's reflected in the upright orientation or whether it's inverted, we have to know what the velocity does. If the velocity goes from a lower velocity to a higher velocity, then as it hits that boundary, right, as it hits that change in medium, it will actually maintain the same orientation. So all I did was consider the velocity, right? If all of a sudden it's going from a thin chord, or it reaches a thin chord, right, and then the chord is thinner and lighter, then I know that the mass would be decreasing, and therefore the velocity would be increasing based on this function, right, based on this relationship. So if the velocity increases at that boundary, again, the pulse, the reflected pulse is actually going to stay with the same orientation as the original pulse did. The transmitted pulse is always going to maintain that upright orientation. So in this case, they both maintain that same orientation, so they are both right side up, if you will, rather than inverting. Question 2, probably not one that hopefully is too tricky to get through here, but we've got a tube that's open at both ends here, right? Or it's open at one end, and closed at the other end. Let's try that again, right? The frequency of the sound that resonates in that is 350 hertz. So I set up both of my tubes here, right? One is open at one end and closed at the other. One is open at both ends. Then I compared the longest wavelength that would resonate in each one. So it'd be 4 times the length of the pipe in one of them, 2 times the length of the pipe in the other one. So if my initial one that was closed at one end and open at one end had a wavelength that was 4L and the new wavelength is 2L, then the wavelength obviously cuts in half, right? And because I'm using velocity equals frequency times lambda, right? If the wavelength cuts in half but the velocity stays the same, the new frequency is going to have to be twice the original frequency, right? So since the wavelength cuts in half, the new frequency is going to have to be twice as big, and so that's where I got my 700 hertz from. So probably B or D were the common options here, and hopefully we're all comfortable with getting D as our answer. Right. For question 3, consider the waves on a vibrating guitar string and sound waves that the guitar produces in the surrounding air. The string waves and the sound waves must have the same. So the key concept here, and this is one that truly is just an understanding question, right? But the frequency for the sound is going to be the same, right? The period and therefore the frequency will be the same for both of those waves as they resonate, right? The wavelength and the velocity are both going to depend on the medium at which the wave is traveling through, and the amplitude for the string is going to be way different for the string than the change in pressure for the compressions in the air, right? So the only attribute, the only quality of the sound waves that are constant are the frequency as it travels between mediums. So then question 4 here, probably one that we did pretty well on as well, right? They give us a pipe that is length 120 centimeters, and then they tell us these sounds of 480, 160, and 96 are produced, but none others resonate longer than this. So what this is telling me really is even if I just focus on that first wavelength there, the longest possible wavelength would be 480, which is 4 times as long as the length of the pipe. And so most of us hopefully are comfortable enough to realize that the only way that happens is if one end is open and the other end is closed, right? That's the only way we can get 1/4 of the wavelength, or the wavelength equal to 4L, right? That's the only way that happens. So if it were open at both ends, it would be simply 2 times the length of the pipe, which is not what we saw here, right? If it was closed at both ends, it would also be 2 times the length. So we do know for sure that it is open at one end and closed at the other, right? So question 4, probably one we did pretty well on. And question 5, I would imagine, hopefully isn't too tricky either, right? They tell us it's open at both ends, so it's basically the exact opposite of what we just looked at for question 4, right? What are the wavelengths of the 3 lowest pitch, the lowest frequency tones produced by this pipe? So in other words, we're looking for the 3 longest wavelengths out there. Well, the longest is 1/2, the next longest would be 2/2, and then the next longest would be 3/2 the wavelength equal to L, and then I just solve each of those, and that's where I get these numbers from, right? So 2L, and then L, and then 2/3 L. But anyway, my guess is 4 and 5 again. Probably we didn't have too much trouble with that. Question 6 does get a little bit trickier here, right? So I'll step you through this if you need my guidance, and feel free by all means to pause the video first and look through my work, and then just listen to my explanations if you need it. But again, this is saving me hopefully a little bit of time here. But anyway, So a thin taut string here is stretched along the horizontal axis, so I've sketched it out there. It says it's vibrating in the third overtone, and the key with the overtone is one more than the harmonic, and what I mean by that is the third overtone is the fourth harmonic. Right, so it's actually the fourth sound to resonate. But anyway, the equation for the vertical displacement is given by this function here. So that's modeling. I went ahead and use my correct grammar there. But I went ahead and wrote down the generic form of that equation, right? This is the equation we saw in class a few times early in chapter 9. And then here's the function that they gave me specifically representing that. What are the frequency and wavelength of fundamental mode? How long is the string? And then see how fast do waves travel on this string. Right, so we want to find the frequency and the wavelength of the fundamental mode, so the first frequency, and then how long is it, and then how fast does it go. So the key is the fourth harmonic would look something like this, right? It would have 4 antinodes as it resonates along that string, right? So then I broke up the equation, the information that they gave me. So since the equation follows the form of 2 times a sine of kx plus cosine of omega t, I know that the amplitude would be half of this, no big deal, right? I know that whatever that coefficient in front of my x, that represents the k, where the k relates to the wavelength, right? So I can use that 14.4 equal 2 pi over the wavelength to solve for the wavelength, which would be 0.436 meters. Keep in mind, though, this is the wavelength of the fourth harmonic, the fourth mode, right? So this is not the fundamental wavelength, this is the fourth harmonic. So we'll play with that here in just a second. But do the same type of thing, right, for my frequency. My frequency relates to my omega. Omega, of course, is 2 pi times the frequency. So if they give me 166, once again, I can solve for that as well, just dividing both sides by 2 pi. Once again, though, that would be the frequency of the fourth harmonic, right? So the fourth harmonic's frequency. So then if I want to find the fundamental ones, I have to make sure that I don't just stop there, right? As you may be able to tell, I initially started to box my answers in there, but we actually want the fundamental frequency and the fundamental wavelength. And so you can start with either one of these, but I took advantage of the fact that if this is the fourth harmonic, right, if this is the fourth mode, then the wavelength is simply going to be right, 1/4 of the fundamental wavelength. As the harmonic goes up, the wavelength goes down, and it goes down by multiple integers there. So again, if this is the fourth wavelength, if this is the fourth harmonic's wavelength, then to find the fundamental one, I just need to multiply that by 4. Right? Alternatively, we do the opposite, right, with the frequency. If I divide my frequency by 4, I find my fundamental frequency. So really, for part A, you could have done either of these first and then found the other from there as well, or you can just do these two separately as I did and then pull them together. Right? Do whichever one you're the most comfortable with. So then finding the length of the string, well, to find the length of the string, now that I know the fundamental frequency, or excuse me, the fundamental wavelength, I should say. Now that I know the original wavelength, finding the length of the string is not too bad, right? Because I know that the length of the string for the fundamental frequency, the length of the string would equal 1/2 the wavelength, and so since I just found my wavelength, I've got that there. I also could just think about this logically the way I did before, right? Again, if the string length here, if this is the wavelength of each wave as it's passing in the fourth mode, I have 2 full wavelengths in here, right? I have 1 wavelength to the middle, and then 1 wavelength over here. So my total length of the string should be 0.872 no matter which approach I take to get there. And then once I know the wavelength and I know the frequency, finding the velocity on the string is also pretty easy. So really for part C, just taking those 2 measurements from part A and multiplying them together. So question 6 here is maybe one of the more challenging questions early on in this homework. So if you do have any questions, if you do have any concerns on this, obviously let me know. But hopefully one that we were able to get through without too much trouble. Question 7 I think is probably pretty straightforward. I would imagine most of us had a lot of success with this. They tell us the fundamental frequency for a pipe that's open at one end and closed at the other. So we know our fundamental frequency is 80 Hertz. We know the longest wavelength would again be 1/4 of the wave. Right? It goes from an antinode to equilibrium for the first time. So since they give me the length of the pipe, I can find my wavelength. And since they're asking for the speed of the sound, I know the frequency, I know the wavelength, I know velocity equals frequency times wavelength. Just bringing it all together and multiplying that out, get about 416. So again, this one's probably pretty easy. I would imagine most of us did pretty well on that one. Question 8, on the other hand, a little bit trickier here. And I think I actually didn't finish this, so I'll explain it as I go through here. and maybe even see if I can write on here as well, although this may just be a highlighter. But anyway, yeah, so I may have to just explain this. So listen closely as I offer my explanation of question 8, because I actually have to revise this a little bit and then clean it up from here. But anyway, so we've got a violin string with 32 centimeters in length and linear density given here. And this hopefully is making you think right away of this type of relationship, right? This is hopefully helping us to think my velocity as a function of tension and linear density. Notice I do have to convert my linear density from grams per centimeter to kilograms per meter, right? So this is the conversion there. That's where my 0.15 came from for the linear density. The first overtone, which is the second harmonic in a 2-meter long organ pipe, is what resonates with that string, right? What is the tension in the string? So I can use that information they gave me about the pipe to help out. So since I know it's the first overtone, again, the key there is that's the second harmonic, right? And so the second harmonic in a pipe that is open at one end and closed at one end would actually be 3/4 of my wavelength equals the length of the pipe. So the length of the pipe was 2 meters. 3/4 of wavelength equals 2 meters. That's where I got my lambda equals 8/3. Right? So that's my measurement there. I can use that to find the frequency. And obviously that frequency is going to be important because that frequency has the same frequency for both the pipe and the string, much as we saw in the question 3 from before. Right? But anyway, so we can find our frequency. So that's all I did here, using 343 for the speed of sound in air, using my wavelength of 8/3. I found my frequency for both the pipe and for the string. Here was the mistake that I made. The string is actually, it's going to resonate here at its fundamental frequency. It's not resonating at its first overtone, right? It's the first overtone of the pipe. It's actually going to be the natural frequency or the fundamental frequency that the string resonates with. So this should have actually been, since the string is 0.32 centimeters, the wavelength would actually be, right, 1/2 the wavelength equals that. So the wavelength actually should have been 0.64. So that's a mistake I made on that, which then changed the velocity on the string as well. Right? If I have 128.625 times 0.64, that actually doubles this number here. So I should have, again, amend this as you go through here, I should have had 82.32 as my velocity equals the tension over this linear density squared. And then once I square both sides and multiply by 0.15, I should get that the tension is about 1016 newtons. So about 1020 or 1016 newtons is my tension. So again, I know I didn't have that written down here. Unfortunately, I don't have a writing on this PDF file, so just bear with it, but amend that as we went through. So your final answer should have been 1016 newtons for the tension in the string. And this question, again, is probably one of the more difficult ones on here. So then the last question, or one of the last questions I'll probably get to in this part, and maybe not, maybe I'll get question 10 in here as well. But the first figure down here shows a snapshot at 0 seconds of two waves approaching each other. At what time was the snapshot in the second figure taken? Now there's a couple different ways you could approach this. It is kind of challenging, right, to see the overlap there, because at first it just looks like a parallelogram, right, or excuse me, a trapezoid. But if you look closely, and I went ahead and drew in the dashed lines there, right, you can actually see that this figure comes from overlapping the triangle and that smaller trapezoid from before. Right, so this larger trapezoid comes from the interference of those two. But probably the easiest way to approach this problem is just to look at the leading edge of either of these shapes. Right, so initially the leading edge here of the trapezoid, right, is at 3 meters. It's traveling 1 meter per second, and by the time we're over here, the leading edge of that trapezoid is now at 7. Right, so if it was starting at 3 meters, it's going 1 meter per second, and it's now at 7 meters. Then that tells me it took 4 seconds to travel that distance. Same thing would be true if you looked at the leading edge of the triangle here, right? This triangle was initially at 7. By the time it moves across, by the time it moves over, that leading edge of the triangle is now at 3. Once again, a change of 4, so that tells me it has been 4 seconds. So anyway, these figures after 4 seconds would overlap a little bit. That is why we do, once again, get that larger constructive interference here, so a larger trapezoid resulting from that. But anyway, I'll go ahead and stop the first part of the video here. I'll wrap up the last 2 questions in part 2, and we'll roll on with that.